Reading audit reports is one of the best ways to really improve your auditing game and learn about all sorts of new bugs and exploits. The absolute best takeaway you can get from reading any particular audit report is actually coming to understand the auditor's mindset and exactly how they came across a vulnerability, and understanding new classes of vulnerabilities to actually look for, and understanding exact heuristics you can use to uncover those vulnerabilities when you're doing your own audit. But that is often quite hard to do, if not impossible to do, because auditors don't ever really share how they explicitly came across a finding, what mindset they were in when they uncovered a particular bug or vulnerability. And also, oftentimes there's a lot of context that's necessary to first have in order to understand what a finding is really all about, and really what the root cause and what the heuristic is to uncover that kind of finding. So in this video, we're going to change that, and I'm going to go over 3 past findings that I had in Guardian audit reports, and I'm going to explain exactly what my mindset was and what my headspace was, and what heuristics you can use to uncover similar sorts of findings. And so after watching this, I hope that you learn a few more common types of bugs and vulnerabilities and the corresponding heuristics that you could use to actually uncover them. All right, but first, who am I and why should you care about my thought process when I was uncovering findings, right? So first of all, my name is Owen, and over a year and a half ago, I founded Guardian Audits. And since then, we've uncovered dozens and dozens of critical and high vulnerabilities, some of which we'll go over today. And my goal with all of these videos that I put out, and especially this one in particular, is to distill down everything that I've learned in the processes and the types of vulnerabilities that I've seen, and give them to you so that you can ultimately become a much better auditor than I ever could be in a fraction of the time. All right, so without further ado, let's get straight into these 3 findings. All right, so this first finding here is from an audit that we did for the Bridges Exchange. This is GG3, a finding where somebody can shorten a lock. So the minimal background here is that somebody can have a lock, if you will, for their tokens, and it will basically hold a locked position of some tokens, right? And that's really all the necessary context here. And so here in the description of the finding, we can see in the transfer lock function, the to stake until is set to the from stake until. Therefore, it is possible to shorten the lock period by transferring from an address with a shorter lock to an address with a longer lock. So let's have a look really quickly at the vulnerable transfer lock function. So here, this is what we're talking about. We grab the to storage, which is a part of the user info, and then we manipulate the stake until to be the from stake until. And so the idea here is that, of course, you could have a to address which has a really long lock, right? It could be 2 or 3 years in the future, and the from address could have a very short lock, right? It could have a lock of simply 1 or 2 days. And so this way, the stake until for the long lock could be magically unlocked in only 1 or 2 days, or even potentially shorter than that. And so that is exactly the net result that is described here. And so when we're talking about uncovering something like this, really the heuristic that can be used here is to simply think about, when we're assigning a state variable to a new value, we have to think about what are all of the potential edge cases here when we're touching this piece of state, right? So obviously in this particular exploit, it's quite obvious knowing after the exploit has already been pointed out, but there might be cases or types of vulnerabilities that are like this that are not as immediately obvious. And the only way you'll be able to uncover them is if you look at a piece of state being changed, like this to.stake until, and imagine all of the different cases. Can I set it to 0? Can I set it to, a very, very large number? In this particular case, can I set it to something that is less than the current 2 stake and toe? And in this case, you could. And in this particular case, that is a very high impact vulnerability. It potentially invalidates the entirety of the potential locking logic. Okay, great. Next up, we have a finding from an audit that was done on Reliquary from the Byte Masons, and this is RLQ4, and this one is about truncation avoidance. And so with this one, I think it would be helpful to first go ahead and look at the lines of code in question here. So all of the context that is necessary here is this is simply a helper pure internal function that is used to get the weighting associated for some reward distributions, right? And it's not exactly important, what the rewards are or how they're being distributed, but what we're going to focus on here is this if and else branch right here that I've highlighted. So we can see that they have interestingly sort of split up this case, and if you do the math here, if you look at the difference between this branch computation and this branch computation, this is actually, if you ignore any sort of precision loss or anything like this, this is computationally the same calculation, right? In this branch here, we're taking the added value divided by this fraction, so the added value over this, versus the old value over this, and then we do the 1 minus that to get the remaining, so it would be equivalent to the added value over this, right? So the reason that this was broken up in the first place was to avoid precision loss in the event that, for example, this fraction here were to be rounded down. And so if you actually go ahead and work through this, we'll find that in this if case, they're checking that the added value is less than the old value. So we know that the added value is the smaller of the two here. And then what they're doing is they're putting this added value in the numerator. And so this is opening this smaller of the two values up to precision loss. So it's actually doing the exact opposite of what these if and else branches are meant to do. As you can see in the else if branch, we have the old value. If the old value is less than the added value, then we take that smaller value and we divide it in the fraction. And so when you're working through if and else if branches or computations like this, where we have some sort of values and we see, okay, we're dividing by a smaller value here, and it's not exactly clear if this is helping with precision, if it's not helping with precision. But one way that I like to be able to understand this type of logic and really sort of make it cohesive and very clear, distinctly manageable to pick apart is I like to take some extreme set of values to really understand how the things work without having to think and allocate too much of my mental capacity to understand it. So what do I mean by that? I mean, let's consider some values like if the added value is 1 way and if the old value is 1 ether. This will make it very clear as to whether or not we are protecting against precision here. So if my added value is 1 way, if this is 1 way and this is 1 ether, of course 1 way is less than 1 ether. And of course nothing is 0. So we're going to go into this if branch here. And so when we're computing weight new, we're taking this 1 way value, multiplying it by 18 decimals. So this is now 1 ether up here. And then this is 1 way here and 1 ether here. So in the denominator, we have 1 ether and 1 way. And in the numerator, we have 1 ether. And so this actually rounds down to 0. However, if we were to have taken those two values and let's say that we had, flipped these signs so that the added value is greater than the old value, then we go into this case. And then this is the opposite, where the old value is greater than the added value. We go in here. Now let's consider the same set of numbers, only entering this else if branch. So we still have added value of 1 way, old value of 1 ether. So this is 1 ether times 18 decimals divided by, you have basically 1 ether and 1 way. So now this is a 1 ether that has been multiplied again by 18 decimals. So there is certainly no rounding down to 0 or anything like this here. So we get that weight old. And then what we do is we subtract for the weight new, we do 1E18 minus that weight old. And so this is going to end up giving us a more accurate weight new, because we're not getting any sort of rounding down to 0 here. And so if we go and read the description now, we can see that this is exactly the example we use to make this abundantly clear, right? So if old value is 1 way, but added value was 1 ether, so I think it's actually the flipped of the example we just looked at, the else if branch would be entered, weight old would be rounded down to 0, right? So if the old value is 1 way, this is going to get rounded down to 0, and then the weight new is going to be basically this minus 0. So you're not going to get any sort of precision here. And then of course, vice versa for the other branch, and of course the other scenario as well. So the recommendation here was, of course, just to flip the logic in these branches, right? So in the case where the old value is the larger thing, then you want the larger thing to be in the numerator here. And then in the opposite case, when the added value is the larger thing, you want the added value to be in the numerator in that case. So when we're purely looking at heuristics and trying to understand these types of things and see how you might be able to find something similar to this in a future audit, first of all, it's simply not shying away from the sort of seemingly higher effort areas of the code to understand. So I mean, first of all, on a first pass, this is definitely not something you would want to dig into right away. But a lot of times when you look at a function like this, maybe your eyes might gloss over at first, but taking the time to actually walk through each of these different cases and actually go through and take some examples and work with them and actually plug in values and see, okay, how does this thing behave when we put in this and we put in that, and really focus on these exact truncations here. Not on your first pass, but on future passes of the code, this is something that you absolutely want to work through computations like this and really understand how they're behaving over all inputs. In addition to that, obviously, you'll note that it's important whenever you see a division sign to actually be able to verify that, first of all, of course, there are any divide by 0 cases and stuff like this, which is of course prevented by this case here. But then also we have the precision loss facet of things, or the round down to 0 facet of things. And so this is something that you always want to pay attention to when you see a division symbol. And then finally, one key takeaway from this finding is the fact that when you're looking at logic, especially like this, where it gets very nitty-gritty and it becomes literally rounding errors that we're looking at, it often helps significantly to use a really small value and a really large value, or just any set of inputs that are going to maximize the space between something, make something trivially small very, very white and black, clear as day, non-trivial. So in this case, like we did with the example of having 1 way and 1 ether, this is not the most common case, but it is the case that makes the problem the most easy to understand and grasp, right? And it's also the most explicative case that is helpful to use in a POC, right? Okay, great. And this third finding here is actually from GMX V2. It is the first audit report that we did for GMX v2, a very early iteration on the code base. And this one is global 2, where we're able to delay limit success among many, many other things because of this underlying bug. So let's just have a look at the code, and then we'll have a look at the exact finding description. So we'll see here in this execute order function, they have a try catch basically around an execute order function call. And all the context that's needed here is that this function executes an order, as you might think, and they are catching the revert reason for, whatever reason this execute order might revert for. They want to basically catch that and be able to decide if they should revert so that the order can be tried again, or if they should cancel the order so that the order is, effectively canceled, it cannot be tried again. And so of course they need the revert reason to be able to decide if this is an Oracle error, if it's any one of these errors here. And so right here is the key to this finding is in fact this catch statement right here, where they're catching the error with a string of revert, like the revert string, essentially. So can you see the problem here and see exactly what is going to trip them up? I'll give you a few seconds if you want to just pause the video and think about what might get them in this instance here. Okay, so maybe you got it, maybe you're stumped. The key error here is that this revert case, this particular catch, is only going to catch things that match this sort of error selector, right? This one that has a reason string. Now, it's important to note that not all reverts are going to have a reason string associated with them, right? There are custom reverts that won't match this sort of reason string, and there's also, of course, panic reverts, something like a divide by zero, a underflow and overflow, panic reverts, stuff like this, that revert with bytes instead of a reason string. And so any of these reverts are not going to be caught by this catch block, and essentially they're going to actually throw a revert overall. And so if they only want to be reverting for these particular keys here, now all of a sudden you're also reverting for some custom errors, and you're also reverting for panic exceptions. And so now you're retrying on orders that you did not want to retry on. And ultimately what this allowed a malicious user to do is to somehow just make a panic exception happen, or make, any particular custom revert happen such that it would revert here until they wanted to make that not happen by twisting whatever arbitrary knob in the future after they see that price has moved in their favor, and then they're able to make a risk-free trade. And so really that's just all the different knobs that we're twisting after we find this particular crux of the issue to turn this particular issue into something that is, critically exploitable. But really, this is the crux of the issue. And this is exactly as we describe it here. We say the try-catch block in each handler, this is not only in the order handler, but also in the deposit handler, the withdrawal handler, does not catch any errors related to a panic exception or custom revert. This enables a number of bugs and exploits on the exchange. Most notably, it is possible to create a limit increase order that exceeds the max reserved USD, therefore reverting on execution but remaining in the order store. And so this one is basically, I think in this case, this was throwing a custom revert. And of course, that isn't getting caught here, and it's reverting overall on the top level transaction. Then when conditions are favorable, the user can deposit enough reserves so their order gets executed. And so we lay out the following scenario. The current price of Ethereum is $2,000. User A creates a limit increase long for ETH at $2,000 in block 100. So they say, okay, I see ETH is $2,000. I want to sort of lock that price in, if you will, and I create that limit at, at block 100, and it has a USD size larger than allowable. Then user A's order reverts due to insufficient reserves, but remains in the order store. So the reason it reverts is because I created it with USD size larger than allowable at that time, at that point in time at block 100 when ETH is $2,000. And so now I know that I have that order that will be able to be executed at that block. And then now as a malicious trader, I can wait 20 blocks until the price of Ether is $2,100. And then user A makes this order not revert by depositing enough reserves so that it doesn't throw that custom revert, right? So now the USD size is not larger than allowable because user A deposits enough to make that USD size allowable. And so now their limit increase is able to actually execute and not throw a panic exception or any sort of custom revert. And so now it's able to actually go through and it won't get reverted here and it won't get canceled either. And so it will actually get executed, but it will be able to use by, however the way the system was working at this particular commit, this limit increase was able to use the prices from back when Ether was around $2,000. And so essentially the user is able to basically buy Ether at a price of $2,000 when Ether is currently at a price of, X, a price of $2,100. And so that's essentially a risk-free trade. And so here are a few takeaways from this particular finding. So first of all, this is not something that we actually uncovered on just a first pass of this contract, right? This is actually something that we uncovered by writing when we were starting to initially get in and start writing our initial sort of edge case test cases. And so this is something we noticed when we wrote a particular edge case that reverted with some sort of underflow panic exception. And then we realized that, well, this thing is not getting canceled. It's actually the top level transaction is reverting with a panic exception, right? And so the first takeaway here is to write tests for code because and do it early and often, because this is going to help you, first of all, increase the understanding of how the system works as you actually go in and write tests and see how each of the functions you're calling gets executed. But then also, it's going to help you uncover things like this very early on, very quickly, where we're not actually catching all of the particular reverts that could be thrown here in this try. And then now, after uncovering that, this is certainly something that will raise alarm bells in our heads after we've seen that, okay, of course, a try catch that has this type of error selector is not going to catch all the different types of reverts, right? So that's the first key takeaway, is to start writing tests and start playing around with systems earlier on as possible to, start to get that context and understanding and, potentially catch anything really, really juicy like this. And then of course, the second takeaway is to take every crux of, this is the crux of the issue, is this line here. Every time you find something like this, use knobs that you have and your general understanding of the protocol to turn that issue as critical as it possibly can be, just to explicate exactly how bad an impact like this could be for the protocol. And so this way you're clearly communicating the value of the exploit that you just uncovered to the protocol team. And you're also clearly communicating that, look, this obviously needs to be fixed. And of course, it's extremely helpful when you're writing a POC and stuff like this. You can see we have several POCs for this particular bug, and that's exactly what you want to do. You want to come up with the most critical cases possible, and then you want to basically communicate those with the protocol. And we can even see just briefly, we'll just take a look at the POC that we did write for this. We can see we hold off limit position with insufficient reserves. So that's what we're talking about, where there's not enough reserves to execute the order at first, and then the malicious user deposits to make those reserves enough, and then the order is able to execute when favorable. And so without getting too in the weeds here, we're seeing that we create an order. Here's our limit increase order, and it has a particular size. And then what we're doing is we are seeing that when it gets executed, right here, we're reverting with insufficient reserve. And this is a custom error, right? And so this is the top level execute order transaction here, right? And this is not supposed to revert with a custom error at all. If anything, you're just going to be reverting with a string. This is the only way that this should be reverting. It should either revert with a string or it should be canceled. But of course, you can see we're reverting with a custom error, and our order is still there to be executed in the future. Okay, great. So now we move forward 20 blocks or however many blocks, and then now let's say we see the price of Ether as having moved in the direction we want it to. And so basically what we do is we do a deposit so that our order can now be executed. It now has sufficient reserves, so it will not revert with this insufficient reserve custom error. And so now what we're doing, this is all deposit stuff, and then now we can see essentially our order can be executed now. So now essentially all I have to do is make a limit increase order, have it have more than the reserves so that it reverts with insufficient reserves, wait until block 200, 300, whatever, where the price of Ether has increased, and now deposit in so my order can be executed and it won't revert with this custom error. And then now all of a sudden my order can be executed, and it will be executed retroactively at that price when it was valued at $2,000. And so that's really potentially pretty much the most critical version of this bug, and that's why we chose this particular POC, right? Okay, great. So those are our 3 findings I had chosen to go through today. I really hope that you got to see some valuable insights, some valuable things to look for as you're going through the code, some good ways to start thinking about code bases as you're going through them, and overall just some good heuristics to think of and some good vulnerability classes that maybe you haven't seen before. If you thought any of these particular findings were particularly interesting, then go ahead and comment down below what was your favorite finding out of the 3 here, and then also share any of your interesting findings in the past, or share just what's your favorite finding that you've seen in a report. Go ahead and share that in the comments below, and we can see who has some of the coolest findings out there. And of course, if you're looking to join a community of smart contract auditors and learn from everybody else's findings and learn how other people are learning about different audit reports and how people are going through and really upskilling their audit abilities, then go ahead and check out the Solidity Lab at lab.guardianaudits.com, where you can join a community of hundreds and hundreds of smart contract auditors who are just sharing their wealth of knowledge, and join us in team up audits where you can come on and join a group of other auditors who are also growing and looking to participate in a real audit, compile a real report, and get rewarded for real findings that you uncover as a team. And last but certainly not least, if you're still not 100% confident in your auditing skills, I collaborated with several other top tier security researchers in the field to bring what I believe to be the most extensive course on smart contract auditing that there is. And so if that's something that you would be interested in, if you would like to go the paid route, then I think that this is without a doubt most thorough resource on Web3 smart contract hacking and smart contract auditing that there is. And so of course, if you are looking to go the paid route, this is something that I would recommend to you, and you can even take $50 off if you use my link in the description below. But all right, that is all for this time, and I hope to see you in the next one.